Classroom tutorial on kinematics. The topic of this video, Introduction to Kinematics. Good morning, students. Welcome to the Physics Classroom video tutorial on kinematics. The topic of this video, Introduction to Kinematic Equation. And there are just two questions we wish to answer in this video. They are: what are the four kinematic equations and what the symbols in these equations mean, and how do you use these four equations to solve word problems? So, let's get started. Classical mechanics, of which kinematics is a branch of, has the ability to make very precise and detailed predictions about the future state of motion of an object. For instance, if we know some information about the current state of motion, say in the original position and say the speed and the acceleration, we could predict at some later moment in time the actual position of the object. And this is what the kinematic equations are all about. Let's look at the four kinematic equations. Here you'll notice that in the diagram, four equations are listed. On the left side of the equation is a variable, and on the right side of the equation are a collection of terms containing variables. Now, one of the most important things that you need to get used to right away is, what are the meaning of these variables? What do the symbols mean? So, the D stands for the displacement of the object. The overall change position in the acceleration is represented by the symbol A, and the time is represented by the symbol T. In these equations, now you'll notice there is a few V's in these equations. There is a V with a little o after it in a V with a little f after it. This stands for velocities, like V with an O after it stands for the original velocity. In a V with an F after it stands for the final velocity. These are the four kinematic equations, and they all assume one thing, that over the course of motion, the acceleration value that you see in this equation is constant. One thing that you should be aware of is that the appearance of these four kinematic equations may vary from course to course and teacher to teacher. For instance, one of the first things that you might notice is that the D that you see in my equation stands for displacement. In other courses, in other teachers, and other sources may represent it by a delta x, where delta x refers to the change in position, just like D represents the change position. So if you put a delta x into this spot in the first equation, you would have on the left side x final minus x original, and maybe you could move that x original over to the right side, and you'd have an equation that looks like this, where the x stands for position x, or x original stands for the final position in the original position. In other equations, we often see a delta x inserted in 4D. In the equation, a second variation that you might find is, instead of seeing T, you might see some delta T's in there. It still means that the same thing the time over which the motion took place, and then you might notice that the V original that I have, the V subscript it, and I'll maybe replace with a V subscript, and they mean the same thing that I just means initial velocity as opposed to original velocity, just a different way of putting it. So these four equations may not always look like the way that I place them here, but the main thing that you need to understand is whatever form of the equation that you use, what do the symbol mean? So here, they are again my four equations. Another thing that you should be aware as of is these kinematic equations or see others, such as your friends, your enemies, or your teachers using these equations is that on occasion there are special conditions that alter the form of these equations. For instance, somebody might be solving a problem in which originally the object starts from the rest. In such a case, the v all terms that you see in these equations end up dropping out of the equation, so they might be written as shown here, so always be on the lookout for a phrase in the problem that you're trying to solve that says starting from rest or beginning in a resting position, because in those situations, under those conditions, the kinematic equations may be simplified to the form that you see here on the second set of conditions that you might come across is an object could come to rest or come to a starting position. In situations such as this, the final velocity would be 0, and anywhere you see the final velocity in these equations, those terms would drop out. So the equations that would change into this form now. Now, if you look at the second equation in particular, that looks quite different than the second equation on the left. What I've done is I've dropped out the VF squared term, and then I swam the 8D over the opposite side such that there is a negative in front of it. You just need to be aware that depending upon the conditions of the problems for which you're using the equations, that the form could be different than what is shown in my original four kinematic equations. A person could make an effort to use this big four kinematic equation and a problem which the object moves with a constant velocity. In such instances, the acceleration is 0. In any term that has I drop in, it will drop out of the equation. But there is another variation that occurs in this situation, and that is if the velocity is constant, then it doesn't make sense in distinguish between the original velocity and the final velocity, since there really isn't two velocities, there's just one constant velocity. So when we have constant velocity problem, the equations turn to this form. You'll notice that the first and third equation have sum, meaning distance equal velocity times time, that just simplify the rate equation that you've probably known for some time. You'll also notice that the second and the fourth equation are not useful at all, certainly. You don't need to know physics in order to tell that the final velocity is equal to the original velocity. When it's not changing, these big force equations are typically not used for constant velocity problems. We just typically use d equal v times t, but we instead use these four equations for accelerating problems in which there is an acceleration, and now we get the useful parts, learning how to use the kinematic equation to solve physics per problem. So what we've seen so far, that there are 5 variables in these equations. but not a single one of the equations contains 5 variable values in it. In fact, each equation has 4 variables in it, 4 symbols, so the strategy that we use to solve a problem is to look through a problem like the one that you see here and try to find 3 known values in order to solve for the fourth variables in request. For instance, here we see 18.5 meters per second, 46.1 meters per second in 2.47 seconds. This is the original, the V final, and the time in what we're looking for is a distance value. So here look, we are going to look for the one equation that has VO, BFT, and D in it. So that's a equation that we use to solve this problem. So the basic strategy will go something like this. First, we're gonna read the problem carefully and we're gonna identify all known values of the above, at least 3 of the 5 variables. In fact, we're gonna write down the known values and relate these values to the symbols that are used in the equation. For instance, we might say something like the original equal 15 meters per second, and we're just gonna identify the unknown variable. I'm gonna write it in a symbol form. For instance, we might say find the D. Now that you have 4 variables, 3 with known variable values and 1 with an unknown value. You're gonna look through the list of 4 equations and find the one equation that contains these 4 variables. Once you've found it, write it down. Then you're going to substitute the known values into this equation, and you're going to use some algebra and some calculation to solve. For the unknown variable, sounds easy, right? But doesn't. Well, so let's give it a try. So here's our example problem, and what we're going to do is we're going to use the strategies that listed here on the right side of the slide. In order to solve this problem, and the first step of the strategy is to look through the problem and identify 3 variables whose values are known. So a car starts from a rest, and I see that starts from rest, and that's indication of kT. To me, that the original velocity is 0 and decelerated over time of 5.21 seconds. So I know that the time for distance of 112 meters. So I know a distance, and so what I'm asked to do is to write these things up and equate the values to the actual symbols used in the equation. And you see how I've done this right. There's that step 1. Now, I look for what I'm trying to find, identify the unknown, and write it down in symbol form. And I'm looking for the acceleration, determine the acceleration of the car. So what I do is I write down an equal question mark, write down a equal question mark or find a or something like that. Now I have 4 variables, and what I'm going to do is find the equation that has these 4 variables in it. So here's the list of 4, and I'm looking for the one equation that has the original D in us. So just start at the top of the list and go down from the top to bottom looking for C. To see which equation has these 4 variables in it, and then you know it's the top equation, so I'm gonna write the top equation down, now we get to step 4 where I substitute known values in the equation, and one thing that you notice is that the original velocity is 0, so that means that the term that goes v all times t is actually going to cancel out the equation, is going to simplify to d equal 1 half a times t. So I take my value for d and I take my value for d and I substitute it into the equation now. Now I'm going to do some algebra and calculation to solve this unknown value acceleration. I'm just gonna make sure I follow the rules of algebra. When I do, I end up getting the acceleration to be 8.25 meters per second squared. And that's how you use this strategy to solve a kinematic problem. Now there is one final caution that I like to give you. In this equation, we see displacement, velocity, and acceleration of all three of these quantities are vector quantities, and just like any vector quantity, they are more than just a number. They have a magnitude or numerical value, but they also have a direction in often time. Directions are represented by plus and minus symbols when we're using math, so it's very important to include the directional information in the equations when you're solving for an unknown. For instance, here you see that the car is approaching an intersection at 24 meters per second, and it breaks a step, so I know an original velocity and I know a final velocity, and I'm told that the car is losing 8 meters per second every second. Determine the braking distance, so when I write down the known variable values, I'm going to have to be very careful because this acceleration value is in negative 8 meters per second. So when I do this problem, it's important that I substitute in negative 8 in the place of when solving for my unknown distance. Well, we've done it. We've accomplished the purpose. We now know what the four kinematic equations are and what the symbols represent, and what we have fairly decent idea as how to use the equations in order to solve physics grade problem. It's at this point in this